Yeah, cool. So welcome back. Let's continue basically where we left things yesterday. I guess all familiar faces, so we can probably jump right into. So today there is a one-word change in the title, and maybe we are switching gears a little bit. So that's now partial differential equations. Yesterday was ordinary differential equations. So today we are going to the real stuff. I guess I don't have to ask, but who in the room likes PDEs? Or loves. I mean, you can also, I mean, there will be no everything plus. Okay, who of you sees PDEs where other people don't see PDEs? At least sometimes. Okay, so that's an argument I will probably, I mean, I often run into. I think today is kind of, I'm preaching to the choir here, but oftentimes, I mean, some people like if you bring in PDEs or views from PDEs into their problems, and some people don't. I'm happy to pick up any fights here. So let's see how that goes. So here's the plan. So first of all, as a warm-up, we'll go briefly through the connection of deep learning and optimal control. Then yesterday, remember we talked about stability. We didn't talk too much about generalization, but I'm going to show you a few pictures. So that's going to be skipped. If you have missed it, sorry about that. But there's a way to go backward in time. So time reversal at IPAM is possible because the talks get recorded, so you can go back, watch that. And that is the main body of work today. So I want to link now convolutional neural networks. So remember, yesterday I did not make any assumption about what kind of data you have. I mean, I showed you these 2D funny little pictures, but in some sense, this ODE perspective you can apply to any ResNet on whatever data it's working on. Today, I want to go to convolutional neural networks. So that's basically where all the linear operators are based on convolutions. And those ones are used for, say, image, speech, or text data or something like that, where the feature space offers you an additional structure. And that structure is the one that we are going to exploit to relate what's going on to PDEs. And then once you have this connection being set up, then really you go through the ABC of PDEs. So you can think about, can I build a network that is kind of like a parabolic equation? Yes, we can. I'm going to show you. Can we build 1 or 2 or 3 or 4 that are hyperbolic? Sure, I'm going to show you a few. Can we do other things than forward Euler? Yeah, we can. And also, this one is a funny note on a little bit of reducing the computational waste in CNNs these days. And it's kind of motivated also by PDEs, of course. So that's the plan. Let's see how it goes. So again, yesterday, so for me, that's the graph-free zone here. Although I very much like Patrick's talk, but today, I mean, no more graphs. So we are talking about these kind of models. And now, later on, so these KJs are the guys we're going to talk about. So I think I mentioned yesterday in passing that these KJs, so that's a matrix that you're going to learn, you could parameterize with a few, say, stencil elements or so in CNNs. Or you could parameterize it also in many other ways. If you think about this trick that I played yesterday to say we are learning K minus K transpose, that if you kind of work that through, you could even parameterize that as one K. That is a K that you build so that it is anti-symmetric. But today, the structure we're going to care about are convolution operators. This is a double click today. So we ended up yesterday having this continuous version of the optimization problem arising in machine learning, and we have this ODE here. Okay, so this is the ODE from yesterday. Today we are going to make this a PDE. And then, I mean, you know, we typically would reduce the objective function, so we would eliminate the constraint and plug the solution into here. But we know that we have a mechanism to compute it via the discretized ODE. So still, we first discretize and then we optimize. So that's also the slide from yesterday. I want to make one more comment here because Tom made a really good comment yesterday asking me about, so why on earth is this trajectory or this movie so smooth? The answer is because we made it so. So, of course, one thing you can already learn from the optimal control community. So you have this theta vector that is a time-dependent function. So guess what? I mean, you can study the regularity of theta over time. Okay? And most of the time we favor systems that don't change radically. I mean, controls that don't switch on and off on a very small time scale. So what we do in the training is we penalize time derivatives of this theta, so that we basically favor smooth dynamics. Okay. I forgot to say that yesterday. And sorry, there's no slide, but I think it's an idea so straightforward I can just mention that. Okay, so in terms of the map, we are now in this top corner where it's very lonely. But that's the PDE motivated approaches. So first of all, I want to highlight a few challenges in CNNs. I mean, I know CNNs have been incredibly successful, and I don't want to take away from that. But oftentimes, especially when I give this talk to mathematicians who have heard about CNNs, and you can learn anything with CNNs, and they are so efficient, I just want to dampen expectations sometimes. So there is a lot of computational challenges, because if you realize a network has a width and a depth. I had this goofy example yesterday where we added a new dimension. If you talk about images, you talk about channels. That's the currency for measuring the width. So an RGB image has 3 channels, but then your hidden features may have more channels, typically more channels, not less channels. Okay, and you can have in the hundreds of channels in some architectures. And then you have the depth. So say you have 20 time steps and a width of 16. Guess how many convolutions you need to compute in a forward pass? Around 5,000. Let's say you have 2-dimensional images, 2D convolutions per image that you evaluate your neural network on. How do I get this number? Maybe I remember. I think it's 16 squared times 20. Because it turns out that in order to propagate this image 1 layer forward, each of those 16 channels gets convolved, or to produce 1 output channel, each of these 16 channels gets convolved with 1 convolution operator, and then they get all summed up. It's called fully connected across the layers. Okay, and then you do this by times 20 and maybe some math errors, but you roughly end up at 5,000 iterations, 5,000 convolutions per image. And before this guy, that was almost impossible. Then, I mean, yesterday I hinted at the memory consumption, because we need adjoints and we need to store intermediate states. So if you say you have 5,000 training images that you're interested in, and you have 32 by 32 pixels, and you pipe them through all at once, you have a really big batch, then you need a lot of storage. So probably this guy is not going to work anymore. And then the big questions are the architecture, design, and interpretation. So I mean, we want to build CNNs that are easy to train, generalize well. They should be difficult to fool, and I think we also probably agree that the CNNs ideally should give us uncertainties and explain reasoning. And a shocking example is this picture here I think it's from a self-driving car. And on a sunny day like yesterday, it works perfectly. And on a cloudy day like today, maybe not so much. And these are definitely things we need to do. And that's where I think there's some room for more research in any of those areas. Okay, let's go into some details. Let's connect convolutions and PDEs, because that's going to be the main argument I have to bring here. So let this bold y be a 1D grid function. So what I mean by that is we have an underlying function y, and we evaluate that function on a grid. And my assumption is I have a regular grid. I mean, not like real PDE persons. We have a regular grid, n cells, hx is a cell size, okay? Then what does it happen? What does it mean to do k of theta times y? So now, I mean, I'm parameterizing my operator through this stencil. And here I assume that my stencil has 3 elements. If you open up machine learning papers, then either they have 3 by 3, or stencil with 3 elements, or 5 elements, or 7 maybe, something like that. But a small number compared to the number of pixels typically. So you don't have like fully supported, and in many cases. I mean, there are some exceptions, but mostly you work with those compactly supported stencils. So this is kind of the stencil. You slide over your vector y, and then you take theta 2 times this current point, and then theta 1 times the left neighbor, theta 2 times the right neighbor, and you add them up to get a transformed image. I can write this much more complicated by doing a change of basis here. So rather than just applying this one filter here, I can write this one filter as a linear combination of these three ones that I picked, okay? But I picked them to make a point. So if we look at them, the first one is 1 to 1 divided by 4. So there the interpretation is that this one, especially as the image becomes finer and finer and finer, does nothing. It's kind of like an identity, or like a little bit of a smoothing that happens here, right? That's what this filter does. The second filter here is minus 101 divided by 2hx. Who recognizes this one? Okay, it's a central difference approximation to the first derivative. And the second one here is the standard minus 1 to minus 1 divided by hx squared. So that's a second order, or discretization of a second order difference operator. So I picked these three. I mean, of course you can pick here forward difference, backward difference, whatever you want, but I picked them so that for h goes to 0, this is actually a basis, so they are linearly independent. If you do other choices, sometimes you don't get that lucky. And of course these betas here and these zetas are kind of related. So you can solve a linear system here if you don't believe me. And for any age, or for any small h, this is going to be an invertible matrix here. So it's a one-to-one mapping. So what that means is that if I think about the limit of n goes to infinity, so I have an image that has infinite dimensional, like a function. Then I can think about the convolution operator as consisting of an identity, a first partial and the second partial derivative. And these three operators are kind of averaged together by weights that are learned, because these betas here depend on the parameters that we are training. So it could be that your network learns in a way that there's only a beta 1 here. So then it's basically like an identity operator. It could also turn out that it's a first order PDE operator or a second order PDE operator. And this property can change in time. So you can have a few time steps where there's nothing going on, like an identity, then there's some higher order derivatives that come in. And so that is just, to make us conscious that, we could interpret the convolution operator as a linear combination of differential operators. And the weights of the CNN determine the properties of the PDE that you're going to get. And depending on which class of PDE you are in, you realize that many properties of even the discrete forward propagation might change. So stability might change. Also different PDEs are typically solved with different numerical methods for stability, and so on. If you have multiple channels, then this gives you a coupled system of PDEs. So there's kind of, I think about it as one PDE per channel. And then they all talk to each other based on how you build your convolution operator. So that's a system of PDE. Okay. So what can you do with this interpretation? So in some sense, what I'm arguing for here is that we should at least, as a guideline, think about the continuous operators on images. So that makes you independent from the resolution, for example. So typically you have in deep learning, you have a given image resolution that you pipe into your network. But it may be that, for example, at training time, you have a really big computer, you want to have high resolution, but then you want to deploy the network on a smartwatch, you have low resolution. So do you want to evaluate the high resolution network on the smartwatch? Probably not. So you want to not lose this information that coarse and fine are related. And one way to do that is what's called multi-resolution learning. So exploiting images at the same image at different resolutions is a very ancient trick in image processing, I think. First of all, to be fast, and second of all, to be kind of robust sometimes. So if I ask you to classify what's in that image, at 12 by 12, no one that hasn't seen this one gets it. At 24 by 24, maybe some people have a guess if they know what the options are, and I forgot what the options are. But at 48 by 48, and with a double click, of course, it's a spoiler. I think at this resolution, we are pretty confident that we can see that this is not a cat, right? If we want to classify this image. So how about we pick this level here, and we train a CNN on that level. So let's have a small argument how that would work. So in order to do this, I would restrict the image size a few times. I would probably not restrict it 4 times, because here, even with my eye, I don't have a sense of what's in the image. So maybe that's a hard thing to ask for a neural network. But this resolution seems fine. Then I randomly pick weights. We talked about that yesterday, that finding good weights is not always easy. But let's randomly pick them. Then we optimize the network based on this coarse data. That'll give us some solution. And all then we have to do, if we want to go to the next finer image scale, we need to kind of do something with the theta, and maybe sometimes we do have to something with the W. So that's all learned weights. Okay, that's a prolongation. So yesterday the prolongation was probably super easy, because if we add layers, I mean, you just interpolate in time. Here, actually, the question is really what do you do with the kernels? So you have a 3x3 convolutional stencil. If you apply that to a coarse image, and if you apply that stencil to a fine image, what are the chances that that gives you the same thing? Almost 0, I guess, in this framework, because you realized from the previous slide that the stencils had this, at least the first and the second derivative had this 1 over h and 1 over h squared. So if h changes, the balance between those stencils also is going to change. So you need to do something. One thing we've done is we looked into multigrid methods. So has anyone done multigrid? Cool. So quite a few. But for those who have not done multigrid, here's a short, very, very short story. So and when you want to solve a very finely discretized PDE, turns out that it pays off to go to a coarser grid to accelerate convergence every now and then. I mean, for elliptic PDEs, that's particularly true. So you have k small h, which is a very fine operator, and you want to build a coarse operator, k big H, that is smaller in size and has different convergence properties. And the way you can do this is you can basically define a prolongation and a restriction operator, so that if you think about hitting this with a coarse mesh quantity, it gets prolongated, multiplied by the fine mesh operator and restricted. And you can design them so, or you can design the coarse mesh operator so that basically the coarse mesh operator bypasses this prolongation fine mesh restriction. So it's much cheaper if you have the same sparsity pattern. Okay? So typically in multigrid, you are given a fine mesh operator, you're given restriction prolongation, and your goal is to build a coarse mesh operator. Here, kind of the way that we're interested in is the other way around. I mean, I want to give you a coarse mesh operator and I want to get a fine mesh operator. That is still possible. So here's a diagram maybe to illustrate this. So if I give you a very coarse MNIST image, and so say I've trained it on fine images first, so I have a fine version of this, and this is my convolution stencil that I want to apply. I want this diagram to kind of give me the same result if I go from coarse to fine, apply this stencil and restrict, or just take this image and apply this convolution operator. So that should basically be equality. That's what this equation here says. And so once you tell me how you want to prolongate, say with a bilinear interpolation or a cubic interpolation or something like that, and how you restrict, typically you do something called a Galerkin projection, so you have a multiple of the P transpose for the restriction. Then this stencil and this stencil are in a one-to-one relationship. So there's a linear system that you can solve to get from here to there. And same way, if you multiply with that matrix that is involved, you can get from coarse to fine. So that's called algebraic multigrid, because you derive algebraic equations. So there's 9 by 9 linear systems that you need to solve, or 9 by 9 matrices that you need to multiply with to do this rescaling. And if you haven't noticed, so this stencil here looks different than this stencil. Okay? And that's kind of the whole idea, that you don't just take the stencil and apply it to coarse images. So just to see that this idea is not completely nonsense, we resorted to MNIST. We've done 2 experiments here. So we took the MNIST and we used fine mesh images, and then we downsampled by a factor of 2, so we get really, really coarse images. So for each of them, you train a network until you hit the state of the art. And then you do an experiment. So the first experiment is, so the fine network here is trained to, well, what is it, 99% or so, I don't remember, but a good accuracy. And then say you want to classify a coarse image. If you just don't do anything, so you take the coarse image, you prolongate it, and you put it through the network, you get to about 84%. And if you do the restriction right, then you at least get a little bit of a boost. I mean, it's not an impressive number for MNIST, but there was no training on the coarse resolution. And also, you see that the prediction, even by the trained network, is very resolution dependent. Okay, and you can go the other way around. So you can train on coarse. That's probably the more interesting one. So you train on a coarse level up until this is well classified. I think there you don't get quite to 99% because you have very coarse images to deal with. And if you just take the network as is and you pipe through fine images, that doesn't really buy you much. But if you do the prolongation of the stencils right, then in this case we got some small boost. Yep.
But often in these, even the convolutional networks on here, at the very top, they often do a non-convolutional operation. You toss a fully connected layer on top.
In the very end, you mean?
Yeah.
Yeah.
And so, did you do that here? And so, then how do you deal with it in the coarse to fine transition?
Well, so here we have. I think we have not done a fully connected layer in the. No, we have done a fully connected layer, if I remember correctly. So you have an output image, and then you do, yes, we had a fully connected layer multiplying with that to the 10 classes that come out. So each of those, actually it's interesting, each of those columns or rows of this weight matrix has the size of an image.
Right.
So it actually is an image.
Yep.
So what we did here actually is to, in the regularization, make it a smooth image. And then you can prolongate and restrict that straightforwardly.
Okay.
But you could also do this usual thing that you just average each channel. Then you're resolution independent, of course. But no, otherwise, that's why on the previous slide we had this prolongate the W. So, but that was a very early experiment that we've done. So after then we learned that basically what everyone does is average all the channels to be completely translation invariant. Because our classifiers here, actually each of the rows actually looked like images, which back then we really liked, but it also means that you're very position dependent. Yeah, that's a good point.
So what is the performance you could get with coarse MNIST?
I mean, it was in the mid-90s%. I mean, it was not bad. I mean, from what I recall. So
would you say with this in this first step, you should be able to get close to the maximum performance? If you train
yeah,
on
I mean, here we tried our best to get the maximum performance that we could find.
But your filters are probably then how big are they?
So we had, let's see, so we have a ResNet, we have 6 channels only.
Right.
So we have an opening layer that's typically a single layer neural network that gets us from 1 to 6.
Yeah.
And then we had just these how many time steps we don't say. Oh, too bad. So then we basically have these 2D convolution layers with 10H activation and softmax.
Size
3 by 3.
3 by 3?
Yeah. So we always kind of use 3 by 3 in these experiments because if you think about this connection between the convolution stencil and the PDE operators, if you go to a 5 stencil, then you can also make a PDE connection, but then you have really high order derivatives in there. I don't know. At some point you have to make decisions, and for us the decision was this doesn't feel right. We don't see, like when you look in image processing, for example, people oftentimes stop at second order operators. So we said, okay, let's stick with 3. And also you realize that if you apply this twice, then you basically also get higher order derivatives if you want.
But if you do 3 by 3 on the fine, and then you go to coarse, do you have anything left to work?
That's a good question. So it's actually a good point I should have made. Sorry about that. So yeah, so if you have, say, 3 by 3 on the coarse level, and you think about this in like spatial dimensions, like how big the domain is, and you go to then a 3 by 3 on the fine mesh, then the region of coverage actually shrinks. Right. I mean, that's with a difference operator, that's also the case, right? If you decrease h, you evaluate the function at more nearby values. If you go the other way around, so we always enforce this to be 3 by 3 and this 3 by 3. If you go from 3 by 3 to 5 by 5, then this mapping here may not be unique. So the uniqueness comes in through the restriction of having 3 by 3 stencils, both on the coarse and on the fine. And yeah, the support is very different then.
So but so that basically means you're putting your kernel on a larger chunk of the image. Right?
Yes.
When you go from fine to coarse.
Yes.
So then basically you're really making a non-trivial. It's not really a prediction, but like extrapolation.
Yeah.
Sense, right? Whereas if you had a 5 by 5 kernel to begin with, you could essentially keep the size.
Sure. You could keep the size, but you couldn't represent all the PDE operators with that smaller stencil.
You can do it in the network.
Yeah, I mean,
Maybe it's better.
Maybe it's better, maybe not. So
theory.
Yeah, so I mean, we made this choice to be kind of close to the PDE interpretation. This is the thing, like we see PDEs where there maybe are none. Yeah, if you think about the PDEs and you have some coefficients associated with higher order derivatives on the fine mesh, you will not be able to represent them on the coarse mesh. And that's something we would choose to avoid when possible. Okay, so that's one thing that you can do with this. So then I think I want to go to networks that are kind of motivated by PDEs. So now we branch into different PDEs. So just if you don't remember, so this is like a very simple example of what a heat equation does. So a heat equation, as time goes by, kind of vanishes and smears out all the features in your 1D image that I have here, right? Okay, and now if you think about you train a convolutional ResNet, if you have these 3 by 3 stencils, it is very much possible that this network is learning something like a heat equation. Okay, it may be the case, maybe not. You don't know, because it really depends on the weights that you train. So here are some things that you might want to consider when you talk about learning. So if you think about this heat equation, then the forward propagation is really, really stable. Basically, everything gets smeared out. If we wait for a very long time, everything will be constant. Okay? So that means that theoretically the network is very robust against perturbations of the inputs. I say here theoretically because we have looked into this, but we're having a hard time really quantifying how robust the network is. We haven't really found a really good tool that works for us. The learning problem may be a little bit tricky here, because if you think what the classifier has to achieve here when everything looks the same, it's very hard. So the recommendation would do not integrate for too long. I mean, the asymptotic state here is not really where you want to be. And then, numerical methods for parabolic equations are very well understood and easy to use. So there are multi-scale methods. So for those PDEs, especially, you can exploit different resolutions. It doesn't work for all PDEs. You can do like reduced order modeling or something like that. I mean, there are ways, for example, you could, in this movie here, in the beginning start with a high resolution and then at some point actually go to a coarser mesh because the feature, like the fine mesh features are already gone. So these are things that people do in parabolic PDEs. So how do you, so now of course, I mean, you know me by now, so how do we now make a network so that we know that it's parabolic, if we want that? Here's the idea. So you take the original ResNet, and this had two operators. So it had like a K1 that was inside the nonlinearity, and then for me it had a K2 that was outside. And in the original paper there is even more stuff, like with batch norms and nonlinearities. But if you pick the second operator is minus the transpose of the other operator, then you end up with something that looks like so. And that is a dynamic that we can say is kind of like a parabolic PDE. And why that is? So for example, if you pick sigma to be the identity, so no nonlinearity, and you pick K1 to be a gradient, then the transpose here will be something like a divergence. Then you have a heat equation. You can also, if you have other fancy nonlinearities here, recreate something like total variation, so like nonlinear diffusion processes. And this guy here basically has, maybe this video plays today. So the idea is that with a parabolic network you smear out features. So this is probably not the greatest example of all, but you may see that some of the features kind of vanish, and also the intensity gets dampened. The energy actually goes down in this system. So if you look at, for example, if you want to study stability, one way is to look at the Jacobian, and you see that this one will be negative definite, negative semi-definite. That's a good sign. So you can use various discretization techniques, like a forward Euler method works very well in those scenarios here, and that can give you a network. You can make stronger statements. So yesterday I made this disclaimer that we typically, like, the stability analysis is really, really hard, and there's no reason to believe that the network is stable a priori. For this network, it's well understood that it's going to be very stable. And by stable, again, we mean that if we have a solution associated with a perturbed input image, then the norm of the perturbation is bounded by the norm of the initial perturbation, and this constant m here is somewhat related to a Lipschitz constant, and it does not depend on time. So no matter for how long you integrate, you are not adding much to the difference. I'm probably going to skip the proof, but it's a 5-line proof or so that that was with pretty standard arguments. So so parabolic CNNs diminish energies and diminish differences in initial states. And these parabolic-like networks do kind of the similar thing. Okay, so that's one PDE. You may like it or may not like it. It's first of all, we were in the business of creating interesting models. Okay, so that's an interesting model. We'll see later how it performs. The other class of PDEs that people like are hyperbolic PDEs. And here I'm not cheating. So I'm not just playing the video in reverse mode. I'm actually solving the wave equation, I think it was here, forward and backward in time. So if you think about wave equations or transport equations, they are very different from a heat equation. I mean, a heat equation you cannot reverse in time. You can try, but you shouldn't do it. And a hyperbolic PDE, you can play forward, backward all the time. Nothing gets lost. So that might also be cool for learning. So if you want to do that, you can use special discretization techniques. I'm going to show you that again, where you have basically a decomposition of y's and x's. So you have different parts of your feature vectors, and they update each other. And you can use that in adjoint computation, because since you can, remember, you have to store all the hidden features for the backprop. If that is too much memory that you don't have, then in this hyperbolic regime, you can safely compute backward in time. There's a nice paper So there's one paper in the neural network community from 2017 that got some traction, which was a reversible neural network. I think we talked about that yesterday, that not everything that is algebraically reversible should be reversed in practice. So take that with a grain of salt. But there was a really nice paper in geophysics, of all places, a few years earlier. There was a review paper, really, because in geophysics, hyperbolic PDEs and optimization of hyperbolic PDEs is a big, big topic. And people have done literally everything you can imagine to save on costs and cut corners. So that paper is 5 ways to avoid storing and then source wave field snapshots, which means something like hidden states. So there are 5 ways of doing this. That's a nice paper to read. It's very unrelated to neural networks, but you can draw from it. Okay, and the idea here with all these reversible ResNets is you save a lot on memory and you pay somewhat of a price in terms of recomputing. And if the first is, the reward is bigger than the cost of the second, then you win. So here's how, actually, one of these Hamiltonian-like structures that we have. So we have 2 PDEs, a Y and a Z, and they are related in their updates. So then you can kind of write this in the matrix form, and you see that it's kind of like a very structured coupled system of PDEs or ODEs. And you can show that the eigenvalues of this are all imaginary. So if you had constant weights in time, at least, then you would be stable. Or what we typically argue is when those weights change slowly in time, which we enforce by regularization, we should also be in good shape. And you can discretize using the Verlet method, so that's like a symplectic integrator that you should be using for Hamiltonian networks. And here's just an example how that looks like. So here I picked the image as a first component, and then just zeros at the second component. And if you play these kind of videos, then you see that some features get passed down and sometimes also up again. But at the end of the day, you have, you generate interesting filtered versions of your images. And you have twice as many images as you put in here now in this case. Okay? And you can pipe them both to your classifier or pipe them through the network if you wish. Yeah?
So I understand it's like Y and Z are sort of, you can make the link with sort of conjugate variables with Hamiltonians. Like are there certain properties about Z that you can relate to Y, or in practice you just construct this and only care about Y?
We've tried a bunch of things, and they all seem to work more or less. So one idea is to say if you give me an image with 32 channels, the first 16 are Y, the last 16 are Z, and I give you 32 channels back, and you wouldn't even know that I've done this division. That seems to work pretty well. In the beginning, we've also done, we're more conservative here, so that we always said we had, say, if you give me 32 channels, then those are the Ys, and the other ones are just zeros. And then I'm getting you the 32 back and pretend that nothing happened. But we felt like, we have all these features computed anyway, so it doesn't cost us any more to do a backpropagation for them, so then maybe this is more efficient. But to be honest, it's all experimental results. We don't have a really good theoretical feeling for what they mean.
But do you interpret this as some sort of a momentum of Y, or
you could. So if you I screwed up. I actually want to call this Hamiltonian-like CNNs, because we don't really know what the Hamiltonian is. So you can think about making now simplifications where you say that the k's are constant in time, and the activation function isn't there. Then you could really think about, one is the velocity, one is the position, and stuff like that. But this becomes very tricky when you then go to more non-trivial models that you need. But yeah, so there may be some intuition about that. Okay, so that's a second. Let's keep a bucket list. So that's a second, I find interesting architecture that we have. And then there's something that was very liberating for us when we moved from more like PDE parameter estimation to neural networks. Because in PDE parameter estimation, there's always a boss, and that gives you a PDE. So if you do electromagnetics, that's Maxwell's equations or something like that. And you can never argue with that is the PDE. In this kind of area, who tells you what is even if there is a PDE model for classifying cat and dog images, and if so, what is the right one. So one thing we've also done is, that's just the reversibility, but we covered that yesterday. And one thing we've done, for example, is to go to second order dynamics. So, I mean, nobody really, just because the ResNet paper can be seen as a first order in time differential equation, doesn't mean that you couldn't throw a second time derivative and see what happens. So we did that too. So you keep basically, so that's a recurring theme that we always have this, we call it the double symmetric layer. So we have this K transpose K in here. That's always kind of mimicking then these, or allowing you to mimic like wave equations or something like that. And for those PDEs, you definitely don't want to use forward Euler, but you want to use a staggered in time discretization, for example, leapfrog discretization, which is also symplectic and also reversible, therefore. So here you have a very different dynamics then. So you actually, in this plot, sometimes you see the clown kind of come back at right over here. It's almost like the same image. So there's really nothing at loss. You see that there are many artifacts here being produced. So if you think about a wave equation and a heat equation, the images that you get out of a wave equation are much more sensitive to noise. And since nothing gets dampened out really, and nothing gets smeared out. So it's a very, very different type of PDE. And again, if you have a ResNet, you don't know what you're going to get. So here the idea is to make sure that you get what you think you like. Okay, so probably time for some results because people get antsy and maybe we get into an argument. Before going there, I have to make one other really good disclaimer that also was mentioned in some discussions I had yesterday. So a ResNet cannot change the size of the feature space by definition. So what people do then is they have, for example, that's at least what we do, or how we interpret what other people do and then mimic it. So you have, for example, an opening layer in your network that, for example, gets you from 3 to 16 channels if you work on RGB images. And then you have a ResNet block, where ResNet now for me means it could be parabolic, could be hyperbolic, could be leapfrog or whatever, that you can run for some time. And then you have what we call connector blocks. So you have the goal here is to, for example, increase the number of channels and reduce the spatial dimension. So pooling is the key word there. And then you stack a bunch of these combinations together until you have very coarse images and you have as many channels as your classifier would like to see. So when we say PDE model or reversibility, there are a few things that are still not really sound, in the sense that even if this block here is stable and reversible, we don't know how it interacts with the opening and the connector layers. The idea, though, is that you have only a few of those, and in some sense you have infinitely many of these guys. Actually, Eldad Haber, my collaborator, and one of his students have done now a nice work where they designed all these opening and connector layers in a way so that they are invertible. And that is nice. They made it invertible and even orthogonal matrices. And with that kind of trick, you can be completely reversible forward and backward. And since they used, so you can think about many operators that do this, but they use wavelets as a basis. So you also have kind of like a multi-scale decomposition here. So that's a very recent work that they've done this year that makes the whole pipeline forward, backward stable and reversible. So which means that you have absolutely a memory-free ResNet. And they actually got some, the interesting part is they got some good results out of this too. I mean, it doesn't work for everything, but for segmentation, I think they have used it.
But could you instead see this as some sort of multi-scale thing,
yeah,
where you have projection lifting operators? And you have a lifting operator that kind of works.
Well, here, like if you think about the wavelet decomposition, the number of pixels is always the same. So if you give me an image and I make a wavelet decomposition, I get these 4 blocks, like low frequency and high and low and high, and each of them has a quarter of the pixels, but nothing really gets lost. So it's really an invertible operation. And there are other something you can, and it's a multi-scale decomposition tool. So kind of that isn't the idea that you then interpret this as 4 channels in the next ResNet layer and have those interactions. Again, theoretically, I'm not so sure what's going on there, but at least from a it's an interesting architecture, and it's something that is, again, reversible, memory-free, and stuff like that. So they are. I didn't put the reference in here, but I can dig it out if anyone's interested. Okay. So, I mean, I sometimes like looking at these kind of like learning curves. I think Anatoly has hinted at that. So what happens if you increase the number of training images? What happens to, say, the validation error? And this is a confusion matrix. So you want this matrix. So this is an STL10 data set. You want this to have be really nice and yellow on the diagonal. So it means that all the ships get classified as ships. And you want just blue on the off diagonals. And I don't know if you can see that. So if you train only on 500 examples, then you have a lot of errors that you're making here. And then as you get closer, like all these different, so this is the parabolic, Hamiltonian, and the leapfrog. They all kind of, look relatively similar, which maybe even tell you, I don't know, maybe it tells you something about the data set that probably here, what is that? Like trucks and birds are oftentimes very confusing to networks, not so much to people though. But this is consistent across the network sometimes and sometimes not. Like, but they all become better as you add training data. So here are just some test accuracies. So for different versions, so now you can think about playing with a number of weights, small, fine, or whatever. And generally, if you add more weights, you improve. And this Hamiltonian actually pretty consistently worked very well for us. And note that for the same image size or number of channels, you typically have half the parameters because you have, each of these operators only works on half of the channels. So that's way fewer parameters. But yeah, if you look at individual images, so if you pull out images of, for example, I like dogs, then you see some instances that get classified. So here's like a bar plot of the prediction that the networks make. So if you see this kind of color that is associated with a true label, that's a good job. And all of them catch this dog, but none of them catches this one. They all think it's a bird. I don't know if it's because the dog is jumping or not, but I pulled out cases where one of them doesn't get it right, 2 of them don't get it right, and all of them didn't get it right. Again, so what we have seen so far in quite limited numerical experience is that we can make these different architectures and they perform relatively the same in the end, which is maybe comforting, maybe discomforting to people, because it means that maybe the architecture doesn't really matter, or it means that there's at least room so that you can pick an architecture that you like. I'm an optimist, so that's how I look at those things sometimes. So here are more learning curves. So that it's like Cypher 10. What happens if you have more images in your training data set? And here's just a comparison between a ResNet trained from scratch and a Hamiltonian ResNet trained from scratch. And what we oftentimes see here, or pretty consistently see, so for the STL10, is that at a given number of training images, we typically are slightly above the curve here. So that's, I think, also something good. And we kind of, one hunch we have is that this may be related to the stability of the architecture, because if the architecture doesn't need to work as hard to explore all the options that are maybe not even feasible, then maybe that helps. But no theory, unfortunately, until now. Okay, so let's do now something that I find a little bit more non-standard and kind of interesting. So if you work with images, there are 2 different classes of tasks. So one is that you give me an image, a high-resolution image, for example, and you ask me what is in the image, like a cat or a dog. That is a high-resolution input, but a very low-dimensional output that you ask me to give. And I think that is a very different thing to ask for than if you give me a high resolution image and you want another high resolution image back. So think about a segmentation, or think about like depth estimation, or we saw like super resolution or something like that. For some reason, these applications feel very different to me. So for example, if I'm interested only in classifying, maybe I don't really need to compare information for the whole image. I mean, all these architectures that you see in classification are based on the fact that are based on the idea that you downsample the images as you go through, which brings distant pixels closer together, if you think about a small stencil. And then you just put a number out. But if you think about a high resolution output, you always need to reverse that trend, because the user asks for a high dimensional output, and you have to make sure nothing gets lost. So there are these ideas like UNets and other networks that kind of allow to couple images from different resolutions. So we thought about this problem a little bit differently. And the problem that you have with high resolution outputs is also known as the field of view problem. So if you have a 3x3 convolutional operator and you have a high dimensional input, you have to do many convolutions until you transmit or exchange information across the whole image. Think about from top left to bottom right. I mean, it takes you a few convolutions to do that. And that is a limitation that is known in PDEs also, because if you solve a PDE like a heat equation, which has a global coupling with an explicit method, guess what? You have to have many time steps or many iterations until you get there. And also, many people actually yesterday also asked me about what is it with explicit time steps? Why not do something implicit? And of course, implicit is something we really like because it's much more stable. And in this case, actually, also it addresses this field of view problem, but it's also hard. That's why we don't do it. So here the idea was, can we get closer to implicit? So we want to get the stability of an implicit method. We want to solve the field of view problem, as do implicit methods, but not have the whole cost of an implicit method. And here was one trick that we found, is basically you take your differential equation and then you do nothing. So you add and subtract L times Y. Okay, nothing happened, right? It's just in adding a zero. But then you do the following. You say that you treat this new part explicitly in your time step, and you treat this part here implicitly in your time step. Okay? Now we suddenly do something. So we change the ODE. Okay, maybe good, maybe bad. But I mean, the ODE was not really motivated by first principles anyhow. And here's a picture for why that could be good. So here in the first plot, you see a ResNet forward propagation over time. And I put a blue dot somewhere in the bottom right and a yellow dot in the top left corner. And just to see, like, this one pixel really, how well gets this information spread out. And you see that after maybe 20 or so time steps, you see those blobs. You don't see them in the top left. I mean, it's very impossible to see them. So now if you say, okay, I rediscretize my ResNet because I don't want to have 20 time steps. They are really expensive. I want to save on that. I do, say, 5 time steps or so. Then you see that you cannot achieve the same spread out of information. And spreading out information oftentimes is a goal when you have a high resolution output. Whereas when you have this implicit-explicit scheme, you can roughly achieve, theoretically you have a global coupling between all the pixels within one step. In many cases, when you pick this L right. And this L here is picked as a convolution operator. And it's chosen so that it's symmetric positive, at least positive semi-definite. So you think about like a transpose convolution times a convolution. And we picked it so that it's very easy to invert, because convolutions are, basically sparse matrices. If you have the right boundary conditions, in this case it's periodic, you can use FFTs to apply them and FFTs to invert them. So, like, theoretically, the workload here is very limited. Implementation-wise, you realize QDNN also has a say. But it is trainable and it works fine. So this is then the final forward propagation. So you have the yj plus 1. So that's the usual forward Euler ResNet step. And then you add this part here, and you have this inverse in here. Okay. And so now in each time step you need to solve a linear system. But what it buys you is you can say that you can be stable no matter what the time step is that you pick. And in practice, what we do is we are learning this L operator, and we are learning also the thetas, of course. So and yeah, it's not our idea to do this. I should say. It was probably born over there in the math department with Andrea Bertozzi and Carola. So they have done that in image processing. For higher order PDEs, these implicit-explicit schemes are quite powerful to kind of solve those efficiently. So here, with this architecture, we actually had a very hard time finding a good small-scale test case that we can really experiment with. So we made one. That is actually an idea of Keegan, as a student of Eldad's, who has put all the effort into making this data set. So it's called the Q-tip data set. So it's like images of Q-tips. And they vary in 3 different classes. So black, black, white, white, and then black and white at the tips. And the idea is to segment these images. So not to classify, but really to segment and label each pixel in the image. And so here you have orange for this mixed one, then blue for the white one, and red for green for the black one. Okay, so that's the goal. That's the ground truth. And we made a bunch of those. And the idea here is that in order to classify to label all the pixels, you need to compare the information on both ends. So the field of view has to be sufficiently large in order to do that. And then we trained our IMAX net and the ResNet, so that basically have the same base architecture, and is tuned, I think, to give the ResNet a chance. I think it was not complete cheating, but clearly in this case we win. And also we had some other benchmarks on like depth estimation, where especially smoothness-wise, you gain a lot by having these implicit convolution operators in there. Yeah, so that was one quite recent work that we've done here in making new architectures, again, motivated by principles that we know from PDEs. So I want to touch a little bit on these lean convnets. And I want to write out a convolution operator for you. So if you have a convolution operator acting on an image with 4 inputs, and you want 4 outputs back, this is actually what's going on. You have these 16 convolution operators. I mean, I mentioned that earlier, but that's kind of the state of the art. If you think about, you have 100 channels, that's many convolution operators. And if you add more channels, the scaling here is not in your favor. So that's why you see those neural networks with so many big number of weights out there. So, and again, from a PDE perspective, that's a system of 4 PDEs that are completely coupled. Every PDE talks to every other PDE. You rarely see that in physics and in real life. So, like one branch of our work was to see, okay, can we reduce the number of convolutions that we need to do here? And one intuition was, there are equations called diffusion reaction equations. So you have a bunch of different PDE solutions, or particles or whatever, or they undergo some diffusion. That happens separately for each of those guys, and then they react with each other. And that's typically a pointwise interaction. And in those cases, you probably want to look into operators that look like so. So you have a block diagonal matrix where you have convolutions. So that is spatial coupling, but everything that is in a channel stays in a channel. And then you have this operator. This is a Kronecker product, and this is the easiest way to make it fit on a slide. But you can also think about this as a 1-by-1 convolution that is fully connected across the channels. But here it's only that a pixel is coupled to the same pixel location in all the other channels, not the neighbors. Okay, then you can take it even a step further, because in PDEs you don't see people having 3x3 stencils so much. Most of the time we use 5-point stencils, or in 3 dimensions we would recommend a 7-point stencil. And that allows you to drastically remove weights from the network. We were maybe not the first, but definitely the slowest in this branch of work. So there are other architectures called mobile nets. I don't know if people have heard about them. They came out at pretty much the same time with similar ideas. So maybe it's a good idea. And here's what you can do in terms of the learning. So if you think about Cypher 10 and you train as a baseline a full ResNet, that is kind of the state of the art. You have, what is it, like 4.3 million parameters and roughly 240 million flops per forward pass. I mean, you realize also it's very difficult now to measure costs of these things, because you have a number of weights some people care about, you have a number of flops some people care about, and then there's time some people care about. Time is very misleading sometimes, because if you time it on one GPU, it's different than on a different GPU. But the ResNet is kind of the baseline. Now, as you decrease the number of weights, I mean, clearly you're going to sacrifice the accuracy, but you're not sacrificing by too much. And there are many options that you can go. So the MobileNet V2 is quite similar to what we do, but it's made so that you first multiply with one operator and then you multiply with the other operator. We kind of put them all together. That allows you to have one pass through the memory, so it should be much quicker. And yeah, for Cypher 10 and Tiny ImageNet, we also had some results. So this is a way, I think, to go if you think about physics or scientific data sets that, I mean, I guess many people are interested in 3D, for example. These are all 2D images, and from a science perspective, probably these images are very tiny. Like 32 by 32 images is nothing that gets people excited in imaging science. So if you go to 3D, then we hope to leverage these kind of networks up much more, because if you go from a 27 stencil to a 7-element stencil, that's already a huge savings. And then essentially what you do in these convnets, that's maybe also one way I should put it. If you give someone a 2D image and pipe it through a convnet, internally the hidden features are 3D images. So in 3D, you go into 4D. So it's kind of something has to, I think, happen there to make learning really efficient and tractable for more problems. Okay, I want to conclude just with a few remarks and a big picture, because this was supposed to be a big picture talk and I didn't deliver on it. So does anyone know what that is? Okay, because I figured. Okay, but I didn't put it for you, sorry. I actually put it here because, I mean, oftentimes when we go give these talks, it's not so, I mean, you hear some pushback sometimes by people to say, well, you know, ResNet works, so why do you want to make it a PDE? We know already everything about it. And there's an analogy I want to make to a field called PDE-based image processing. And if you look at how this image was produced, of course, you know, it's a lot of effort into measuring really good data. But in the end, also, it's not just, you know, pixel data that gets in. The algorithms that are used to actually generate this image, heavily math-based and actually very much PDE-based and also UCLA-based. So there are a few seminal works in PDE-based image processing, because image processing has been around for many, many years, of course, but somewhere in the 80s, 90s, there were really, really breakthroughs and many mathematicians jumping into that area to take things like, develop things like optical flow, nonlinear diffusion, edge preserving denoising, which is actually the one used to generate this picture, or to segment images. These are all, you know, PDEs that, you know, segment images, at least in principle, and, you know, we can study them. And they somehow generalized what was out there in the image processing community. How did they do this? So it's kind of like a common thread. So first of all, when you want to go into this area, you take an image let's call it I, and you model it as a function. Similar to this grid function that I talked about earlier. So you think about an image as a function from RD, D is your space dimension, to RC. C can be 1 for gray value, 3 for RGB, more for hyperspectral imaging. So that allowed all these works to abstract from the resolution of an image and to write down something in a continuous space and to study the properties of those algorithms. Then you interpret, as a next step, the operations that practitioners do with their image data, so that's a discrete object like matrices or tensors, as PDE operators. And you study what kind of PDEs people are actually looking at. Their uniqueness properties, stability properties. I mean, people have done all these things, and regularity, of course, is a big thing. And motivated by these PDEs, people have like pushed technology for image processing, I think, up to a level that we can talk about images like that. So it's just an analogy. So there's a branch of PDE-based image processing. So we don't feel like that crazy to now think about ODE or PDE-based machine learning, where you can argue, okay, there are these discrete objects. They more or less work. Some people have an intuition how they do their job, but there also is a lot of theoretical backbone missing. And that story of PDE-based image processing definitely not only inspires us, but also inspires many other groups that I know of. So, for example, in the math department at UCLA, with Stan Osha's group, I mean, these people have done a lot of work in that area and are doing now a lot of work and nice work in differential equations and neural networks. So that's just, maybe a small detour and a note before I conclude. And yeah, so really the mission that we have is we want to make CNNs that are stable, well-posed, and efficient to really support scientific applications. Are we there yet? No. Is it going to be easy? No. I mean, if you think about the first paper on the ROF model is from the early 90s, and the black hole images is from yesterday. So I mean, there's some way to go, but it's not. I mean, it's an intriguing route. So. Hope I could entertain you a little bit with these thoughts and can take more questions. I think we have a few minutes for that. And of course, again, thanks to the people who are doing the work.